So let me introduce our next speaker from Argonne National Lab, Shane Snyder. We work with this group very closely, and Darshan is definitely a tool that every developer of parallel HDF5 application should have in the toolbox. So Darshan, please.
Thanks for the introduction, Elena. So as she mentioned, I'm going to talk today about, and you guys can see my screen too, right? Just double checking.
It is in presenter mode.
Oh, yep. There we go. Good point. Can you see that?
Yes.
Okay. Sorry about that. So yeah, I'm going to talk today about characterizing and understanding HDF IO workloads. So for motivation, HDF, as we all are probably aware, offers a really convenient abstraction for large data collections. So whether you're storing, multi-dimensional, multivariate data, it gives you, a lot of, useful APIs that can be, helpful for storing that sort of data. But the difficulty it creates is that it kind of makes it difficult to understand what's happening with lower layers of the IO stack. So if you can see over here on the right side, I've got a figure kind of showing the HDF5 stack for different types of applications, essentially. So at the top, you have an HDF5 application. In the middle, you have different vols and storage system types. So, your traditional MPIO POSIX to file system, or something like Deos to object store, S3 to cloud store. And then at the very bottom, you have your actual storage hardware. So there's just, a lot of depth and breadth to the IO stack, basically. And it creates problems for users not necessarily understanding how their HDF5 IO workloads interact with the lower layers. And as you can see, this might change depending on which vol or underlying technologies you're using. So there's this bit of a disconnect here. So we think that, instrumentation of HDF IO workloads, as well as instrumentation throughout the stack, is going to be critical to understanding and improving use of storage resources, basically. So users could use this information to guide tuning decisions, or facilities could use it to better understand broader HDF5 usage in the wild, and et cetera. So today I'm going to talk specifically about a tool called Darshan that I helped develop at Argonne. It's basically a lightweight IO characterization tool that captures condensed views of application IO behavior. So for every job that Darshan instruments, we're going to produce a summary of IO activity to each file that it accesses. So we'll capture things like counters, operation counts, bytes moved, and things like that. We capture histograms describing different things like access patterns, and we also capture timers. We also do support full IO traces at lower layers like MPIO and POSIX if users are interested in more detail. A couple of, or a few higher level things about Darshan that are important to consider. It's widely available, so many of you probably are already familiar with it, but it's deployed at many production computing facilities. And it's generally on by default too. So at these facilities, so places like ALCF, NERSC, et cetera, Darshan's basically already available to you, and you may not necessarily notice it's there. It's easy to use, so there's no code changes required to get Darshan integrated, and there's negligible performance impact too. So it's really amenable to just kind of leave it on and kind of forget it's there analysis. And last, and probably most relevant to this particular talk, is it's modular. So adding instrumentation for new IO interfaces or storage components is pretty straightforward. So we have APIs that simplify that process. So for how Darshan works, we support both statically and dynamically linked executables. For static executables, we insert our instrumentation at link time, for dynamic at runtime. So we support both modes, basically. Darshan has traditionally depended on MPI, and and those of you that are familiar with Darshan, this might be news, but recent versions 3.2.0 plus, we can also instrument dynamically linked serial applications. So this is something that we're excited about, using Darshan in new context outside of MPI. So things like Python frameworks like TensorFlow or Spark or whatever, we now have capability to generate Darshan logs for that kind of computing. So as the application executes, Darshan will record file access statistics independently at each process. And further, it'll use a bounded amount of memory so that we're not eating up too much of the application memory on the compute nodes. And then at application shutdown is where most of the magic happens, where Darshan collects all the information from the individual instrumentation modules, and we collect this data, compress it, and write it to a log file. For MPI applications, there's an additional step where we reduce records that are shared globally. So if you imagine every process accesses a shared file and has an independent record for that, Darshan will condense it down to one record to save space. And we also use MPIO for MPI applications to write the actual log file. So as you can see over here on the right, we have a simple application stack, and you can see where Darshan's got instrumentation interposed at different layers of the stack that interacts with the Darshan core library, and then at shutdown time, like I mentioned, it takes all this data, reduces it, compresses it, and writes it to a self-describing log file. So for analyzing Darshan logs, we have a couple of tools that users generally get a decent amount of mileage out of. So first is Darshan Parser. This just provides a complete text dump of every counter in a log file. So it provides you a lot of information, but it's not necessarily great for users to get their bearings or something like that. For that, we'd recommend Darshan Job Summary, which provides a summary PDF that kind of describes application IO behavior using different graphs and tables. So I have a few examples here, but bottom left is IO operation cost at different interface levels. So you can see there we have POSIX, MPIO, and standard IO as different interfaces, but we can keep track of how much time relative to the entire application is spent in different API levels and doing what types of operations like reads or writes or metadata. In the middle, we have IO operation counts across different interfaces. So we can keep track of how many POSIX writes or reads or MPIO writes or reads or stats. Just a good way to keep track of the intensity of different operations and different API levels. And then the last one on the right is just IO access sizes using histograms there. So you can see what this one is for MPIO, what size accesses are being generated by the MPIO interface for that particular file. So what you guys are probably most interested in today is the HDF5 support that we've integrated into Darshan. So basically, we want to, as I've kind of already outlined, we wanted to have a deeper understanding of what's going on inside of HDF5. And so we focused on developing a detailed instrumentation module for Darshan that characterizes both HDF5 file and dataset level accesses. And this is similarly available in Darshan 3.2.0, so it's already out there if people are interested. But essentially what the goal was is just to characterize dataset properties and access patterns. And you can also, since we're capturing information on both files and datasets, we can get a picture of how datasets are organized in files and things like that, just to better understand the underlying or the HDF5 workload the application's generating. So yeah, this data is going to be really useful for not only understanding how applications use HDF5, but since we've already outlined we have instrumentation at lower layers through Darshan, it also lets us contextualize HDF5 IO behavior with those lower layers. So we can kind of have some insights into how the different layers are cooperating to handle the IO workload essentially. So we can answer questions like, do high-level HDF5 dataset accesses map efficiently to underlying storage system accesses? If not, are there obvious optimizations that would make sense from looking at the Darshan log data? So would it make sense to enable collective IO or chunking or things like that? That's basically what we're hoping the module will be able to help out with. As for what specifically we can instrument in all the different APIs, I'll just kind of walk through some of the things that we capture. But for HDF file instrumentation, there's not a whole lot. There's not really a ton of API calls in this part of the interface anyways, but things we do capture are, number of times that a file is opened or created, number of times it's been flushed. We also capture whether MPIO is used. So there's a file creation property that you can use. It says use MPIO for this file. So we capture whether users are setting that. And then we also capture metadata timing, which keeps track of the open and create and close and flush operations, how much time is being spent in those. HDF5 dataset instrumentation. This is where a lot more interesting things are captured because this is where the IO is done. So we can keep track of operation counts again, so opens and creates of datasets, dataset reads and writes, flushes, things like that. We can keep track of the total number of bytes read or written at the HDF5 layer to different data sets. We have, again, access size histograms, like I showed earlier, that give you an idea of what size accesses are being made from the HDF5 level. We capture information on selection types. So did the user, for each read or write operation, are they using regular hyperslabs? Are they using irregular hyperslabs? Are they using point selections? So we capture information on that. We capture total dimensions, the number of points in a data space for the file to give an idea of how large it is. We capture chunking parameters for that particular data set. And similarly to the file level, there's an MPIO collective flag basically that you can pass as a data set creation property list that says use collectives for this particular file. So we capture whether that's used too. And similarly, we capture a bunch of timing information on read, write, and metadata. So this is pretty timely given the last talk. So thanks, Mark, for setting the stage. But I was going to use the Maxio HDF5 plugin just to run through a couple of simple examples that we could use to show what types of insights this type of instrumentation could enable. So using Maxio HDF5 plugin, we just ran a simple 60 process 5-node example to a single shared file. This is using a 3D mesh, and it's writing roughly 1 GB of cumulative HDF data. And what we're doing is we're basically just comparing the performance of a collective configuration of this versus independent IO configuration. And you can see down at the bottom, the results here clearly show that for this particular workload, collective is a huge net win. There's a order of magnitude difference between the bandwidths attained and the runtimes. So for collective, you're getting upwards of 300 megabytes a second in like 5 or 6 seconds, whereas independent's taking over 40 seconds and about 30 megabytes a second. So I'll step through these graphs in detail in the later slides here. So focusing first on independent IO workload. You can see that, so just to kind of explain the graph first off, it's almost like a stack. So it starts up at the top, the application level, and you work down to the POSIX layer, and it just shows you how much time is being spent independently on each different layer. You can see here for independent, POSIX IO dominates completely. So over 25 seconds of the 40 seconds of runtime is spent in POSIX IO. So you can see over here on the right, I have different graphs that are pulled from Darshan job summary tool that kind of explain this. You can see at the top there's IO operation counts. You can see that there's basically 5 million POSIX writes that are being generated for this particular workload. And underneath that, you can see, let's see, the POSIX access sizes that are being used. So it's generating 5 million POSIX writes, all less than 1 kilobyte in size. So this is a really challenging workload, particularly for parallel file systems due to latency and things like that. So it's not surprising necessarily that this workload got such poor performance. Another thing you can notice looking at the graph is that HDF5 incurs non-negligible overhead that not necessarily was expecting. And I'll dive into that a little bit more in a couple of slides. The other thing that's obvious is that there's almost, you can't really discern MPIO time here. It's a very small sliver. If you look at the graph at the top for operation accounts again, you can see that MPIO and POSIX are doing identical things essentially. They're issuing the same number of operations, which makes sense. This is all independent, so MPIO is literally just passing through the operations down to POSIX to do all the IO, so that makes sense basically. For collective, this is much better performing workload, and you can see that HDF5 and POSIX are showing much less overheads for this this workload. If you look at the IO operation count graph on the right top, you can see that we've reduced the number of POSIX operations from 5 million down to less than 200. And if you look at the access sizes below that, you can see that essentially most of the operations are on the order of 10 megabytes, which is going to be much more suitable for a parallel file system to give you good performance. Other things you can notice, MPIO collectives, I guess, dominate the runtime of this. That's not really, necessarily surprising, because what you're doing when when you use MPIO collective IO is you're kind of trading off doing more communication in an attempt to generate accesses to the storage system, which are much more performant. So that's what you see here. There's some additional MPIO overheads, but you'll gladly take that to get the IO performance you get using collective IO, essentially. And another thing to mention is there's you can see a few number of MPIO independent operations that happen too, and you can see there's some smaller access sizes that are kind of outliers. Those are most likely just coming from HDF5 writing its metadata and things like that. So going back to the independent IO example, I wanted to kind of walk through quickly the cost plot or graphs like I showed earlier from Darshan job summary. So on these graphs on the right, you can see there's the APIs are on the x-axis now, and on the bars we're showing you how much time relatively is spent in each API doing different things. So in this case, for a write workload, we're just looking at write time and metadata time. You can see that the write time across all APIs is really similar. So that kind of supports the idea that for this independent IO workload, that POSIX is dominating everything, and MPIO and HDF5, there's not really much they can do about it. But what was interesting to me is that this big chunk of HDF5 metadata time, about like 10 seconds or so worth, we were able to look at that in more detail, and 99% of it is being spent at the H5F level. So there's not really a whole lot we're instrumenting there, so that means that this time is almost wholly attributable to open or close. I assume close operations. It's not necessarily a problem or anything. It's just something that's kind of stood out to me as being unexpected, that there's presumably a lot of activity going on at file close time that doesn't necessarily map to what's happening at other layers. So just an observation I had there. So yeah, just want to, I guess, wrap up now. So we're excited about HDF5 integrations with Darshan. We think it's going to enable a lot more better understanding of HDF5 usage on supercomputers, and we're hoping that users can use this sort of data to help pinpoint inefficiencies in their workloads, and ideally help drive them towards better tuning decisions. So as I've kind of mentioned already, this is already released, but that doesn't mean that it's sealed, basically. So we can always add more instrumentation or address any feedback that you guys have. So we're really excited to see if you guys have any thoughts on additional things we can instrument, or better ways of visualizing this data. A lot of the graphs that I presented that had HDF5 data are just kind of ad hoc things I put together for the presentation. These things aren't integrated into our analysis tools yet. So if you guys have ideas on how to do that in a visually aesthetic and useful way, then we would love to hear feedback from you guys. So whether that's in the question and answer section we'll get to in a second, or offline, I have some Darshan users mailing lists, our website, and GitLab and stuff if you guys want to reach out. But yeah, I think that's mostly it. So if you guys have any feedback or anything, I'd love to hear it.
Okay, thank you, Shane. There were a few comments in the chat window, if you can see it. Mark asked to send you, when you have chance, command line you use to get results that you presented.
Okay, yeah, I just finally got it to pull up.
And you do have now Python module, right? So that people can read.
That's right, and that's kind of related to why we haven't integrated the HDF5 data into the summaries, like Greg was asking, is that we just recently are integrating Python bindings to our C analysis library, because people want to write analysis tools using Python, not C. So there wasn't much of an appetite on our team to do a whole lot of analysis tools from the C library. So now that we have Python bindings, we're going to revisit this. And as part of that, we want to make sure we're integrating the HDF5 data into these graphs too. So that's not the current state of the art, but that's what we're shooting for. And we've got better tools at our disposal to do that.
And if Alexandra, you're here, Alexandra Jelinek from HDF Group. We created some Python notebooks to work with output. So Alexandra, and we will be distributing them. So Alexandra, could you please comment on this? if you're there. Okay, probably not, but stay tuned. We have some
No, that's great.
some a notebook, and it's really good. We as part of ECP project, we are doing this work.
I'm glad it's been useful for you guys. I appreciate that.
And there is another question for you.
Okay. Yeah, I think, yeah, there's nothing, we don't do anything below POSIX. So I mean, we can keep track of POSIX access sizes. We can keep track of, whether consecutive accesses are, right after each other in a file. So like whether you're doing sequential accesses to a file, which should generally perform better and things like that. But we don't have any insights into lower layers than that, like block level or information. We do capture some information for Lustre file systems, which is a little bit, I guess, lower than the POSIX API, but it's basically just grabbing striping parameters and things like that. So POSIX is usually the last stop for characterization data for us.
Okay, thank you. Any more questions?
There is one more question from Mark.
Oh, from Mark, yes. Mm-hmm.
Okay. Yeah, so the question is why I think on the IO intensity graphs, there was a huge spike for MPIO collectives versus the independent operations at the POSIX level. I think that's what Mark's asking. I think the part of that is for the MPIO collectives, the operation counts are going to be multiplied by the number of processes. So you have 60 processes doing a collective write, it's going to show up as 60 operations. And if it boils down to one underlying POSIX access, it's just going to be one there. So there is kind of like an amplification factor that may be a little misleading. So I think if you were kind of confused by why there's so many MPIO collectives, I think it's just because it's multiplied by mprocs, I think.
I think he's accounting for that in his mental model, but maybe something beyond that too. Hard to tell. Okay.
Yeah,
okay.
I'll send you the information on the command line I used, Mark. And if you or anyone else has any other questions, be happy to talk to you guys offline about additional details.
Mm-hmm. Thank you.